All right. So how's everyone doing? Somewhat awake? Somewhat with me? So my name is Chandler Carruth. I work at Google. I work on the Clang and LLVM compilers. I kind of lead the LLVM team at Google. I'm one of the people that's working a lot on kind of LLVM's internals and core. I also represent Google in the C++ Standards Committee, and I'm actually responsible for the C++ programming language platform at Google, right? Like what is C++ supposed to look like at Google? And one kind of immediate question that I have to ask myself whenever I'm thinking about C++, I have to ask myself, why? Like, who cares about C++ anyways? What's the point? Like, I mean, I know you guys are all here and you're all really pumped. You guys are really pumped and excited about C++? Like, yeah? No? Oh, come on, people. This is terrible. This whole talk's going to go really badly unless you guys are super excited about C++. Okay. So I'm really excited about C++. I don't know if you guys are. But it's important to not just get excited. You have to ask yourself, you know, the kind of classic questions, so what, who cares, right? Why does this language matter? And for me, and in a real way for Google, the reason why C++ continues to matter today is because of performance, right? It's because of overhead, right? Performance is ever more important in our world. Our devices, right? These little devices that we carry around, thanks to, in large part, Steve Jobs, right? They get ever smaller, they have ever less battery, right? And so performance and efficiency become ever more important in our lives with software. And C++ is the language which is best filling that role. But there's a problem with that idea around C++, and that's that we actually have a hard time writing efficient C++ code. Right? Like, you might look at me and be like, but isn't C++ like the fastest language? It's super awesome and stuff. Yeah, but it's actually still really hard. And there's one particular challenge that our programmers face with C++ that I'm going to try and talk to you about today. And that comes from compiler optimizations. So C++, I've said it in several different talks, C++ does not make your code run fast. Right? There's no programming language out there that can just make your code fast magically. Right? What C++ really does is it gives you control, a tremendous amount of control. But there's something else that it does that's actually really tricky. It also gives you some of the most powerful compiler optimization technology available today. C++ is where some of the most amazing compiler technology goes to try and make your code run more efficiently, to make your code run faster. Unfortunately, it's also not magic. I mean, it may feel like magic, sometimes good magic, sometimes bad magic. I suspect a few people, has anyone here fought with the compiler every now and then and been kind of, yeah, it's okay, I do too. And I want to try and fix that. And I think that the way we have to fix that is to give you, the C++ programmers, I mean, how many folks here work on a compiler? Seriously, I want to see how many hands. Like, come on, I know a couple more people here work on compilers. Okay, so most of you do not work on compilers. There are like 10 of you. And by the way, for the 10 of you that work on compilers, please don't heckle me too much. But I want to give all of the rest of you enough of an understanding of how the compiler, especially the optimizing compilers we use today, work, so that you can actually work with the compiler instead of kind of fighting it. Now, probably get into my slides. So I hate slides, by the way, so apologies if my slides don't make as much sense as what I'm trying to say. So compilers, like famously, how many folks here, this was their compiler textbook? All right. I love this compiler textbook. I don't actually love this textbook, but it's got a lot of good memories. So this is the complexity of compiler design, right? And then we have some tools to help deal with it, data flow analysis. There's other stuff here. Now, when I think about the complexity of compiler design, and really what this book was thinking about in complexity of compiler design is actually the complexity of front-end design. How do you understand programming languages? Ironically, that's essentially a solved problem in compilers today. No one actually, there's interesting and important work there, I don't want to dismiss it, but that's not what I'm here to talk about, right? That's not the pressing need. The current complexity of compiler design is actually how do we optimize the program, right? The optimization frameworks tend to be much more complex than the actual language front ends. And they kind of make me feel like the complexity is a little bit more like this kind of a dragon than this like nice, like polite dragon, right? Optimization is incredibly challenging. And so it's a very complex beast. I'm going to try and walk you guys through it. Please stop me and ask questions as we go along, okay? I want to try and give you guys an understanding of a framework that you can use to think about how your code is optimized so that you can kind of understand what will happen and won't happen and why better, okay? Okay, so the key thesis here is that I'm giving it all away, right? You can go, we're done. But this is actually the lesson. Understanding performance means understanding optimizers, right? You can't not understand the optimizer if you really care about the performance of your code. And so we've got to find a way to actually understand how our compilers are working, right? And to do that, we have to look at how compilers work. So how many folks here have at least taken a compiler class in university? A few people have taken it. Well, that's good. So you might remember some diagram that looks like this from your compiler class, right? We have compiler frontends, right? This is what the Dragon book mostly dealt with. We have this optimizer. We have a code. There's supposed to be another word here, but I told you I hate slides. We also have code generators here, right? We have to generate executable code. So that red Dragon book essentially dealt with everything except this middle. Completely skipped that. This middle piece is the only thing we're going to talk about today. Okay? We're going to completely ignore the problems of generating code, right? Executable code. We're going to completely ignore the problems of designing good front ends. I want to talk about how we actually do optimization. All right, so let's just dive right in. By the way, I'm going to have a lot of code on slides. This is probably some of the biggest code. If you're at the back, you're having trouble reading the slides, please, find your way forward, because there's going to be a lot more code up here. Okay, so we have some code, right? This does some things, right? Like this is a nice little C function. It's not very interesting at all. So you might think, oh, this will be a nice kind of example to step through when we're looking at what compilers do. So I want to compile this, right, and see what the compiler uses to model this. Okay? Very, very simple C program. What will the compiler use to model this? So this is how Clang models this. This is actually about the first, eighth of how Clang models this. This is the AST required, right, hold on. Tiny little program. This is like a tiny fraction of the AST required to model it, okay? So the whole compiler complexity thing, they weren't totally off their base, right? So this is the AST. This is not at all interesting. We're not going to talk about the front end today. Once it goes past the AST, it's going to do something like this. And I know this is too small to read. Don't worry too much about this. But this is actually what we're going to talk about. And unfortunately, in order to understand this, right, which is where the optimizer works, this is what the optimizer works on, we have to understand a little bit about how optimizers are implemented. Okay, and that means we need to take a digression to really describe LLVM, which is a particular optimizer, and its intermediate representation, or its IR. You're going to keep seeing IR on my slides. Okay, so caveat, I am going to talk very specifically about LLVM in this talk. Okay, that's the optimizer I work on. It's the one I'm deeply familiar with. However, the core principles that you're going to see here are not dissimilar between optimizers. The similarities are much greater than the differences between most modern, really advanced optimizers. So I'm just focusing on LLVM so that we have something concrete to look at. Okay, so we need to understand this kind of intermediate representation that LLVM uses to optimize your code. All right, so to understand it, let's start with a truly simple example, much simpler than that big one we looked at. So LLVM's intermediate representation is a kind of distilled form of a program, right? It's as simple as we can make it. So we can declare functions, right? We have return types and argument types. Values, like %x is a value, have types, in this case, I32. Right? We can define a function, f, right? You can kind of pick up on the syntax, but you don't have to know the syntax. You just have to know the core structure here. And then we actually have to define, a piece of a program, right? Logic, functionality. And this is done through a sequence of instructions, right? So we're adding two integers, we're calling some other function here, passing it an argument, getting a return, adding more integers, returning an integer. Folks think they kind of understand what this does? It sums the arguments and passes that to G, takes the result, adds it to C, returns it. Make sense? Not too hard. Cool. This is the most simple form of LLVM's IR. So let's then layer a little bit more complexity onto it. So how do we model control flow in LLVM? Right, so control flow is going to be modeled by a very, very minimalist construct. We just model kind of basic blocks, right, which are contiguous sequences of instructions, right, operations that all happen in order. And then at the end of each of those, we have something that ends that basic block. In this case, it's a BR, or it's a branch instruction, right? May look familiar, right? And when you hit one of these end blocks, it can transfer control flow to some other basic block. So here, the entry basic block has an add. We then branch on a flag. So this is a conditional branch, right? We go in two directions, and this label is how we say what the destination is, right? So this goes to then, we call a function, go to else. Pretty straightforward. Folks have a good grasp of kind of the control flow? Okay, like I said, you got to stop me with questions if you've got them. Okay, so now how do we deal with data flow, right? When we have control flow, how do we deal with data flowing through that control flow graph? And this is where LLVM starts to stand out. LLVM uses what's called a single static assignment or static single assignment. I can never remember which order the S's go, but it's the SSA form, okay? So it's a very, very common representation in compilers. LLVM uses it, GCC uses it, I believe Intel uses it, and IBM uses it. Every compiler I know of uses SSA representation. LLVM uses a very heavyweight SSA representation in that it is only an SSA representation. GCC and other compilers have non-SSA representations. So in SSA, you have this strange property. Once you, so this add instruction, right, it returns some value. It's kind of how we think about it in an imperative context. But in an SSA representation, it doesn't just return a value, it defines a value. And it is the only definition of that value. So this add I32 is the definition of C. And C can never take on any other value. It's an entire function, right? And so we can use C after it has been defined, but not before it has been defined. And this brings kind of a hard problem. How do we use something when it's defined only in a conditional path? And the answer is that we have to have some construct that merges values based on where you came from as you begin execution. And this is the core concept of SSA, and it's called a fee node, right? And LLVM directly represents this as a fee instruction. And the fee instruction has operands. Each of these operands is a pair, which says, where did we come from, right? What predecessor did control flow from? And the value that this fee takes on when control flows out of that predecessor. So if control flows from entry to end, we pick up the value of %C. If it flows from then to end, right, we pick up the value of %D. And now result is defined in this basic block, and we can use result. Make sense? Okay, so this is like your intro compiler class, but for optimization. We're just blazing. All right, so this is, here's the scariest thing to me for LLVM's IR. I mean, there are a bunch of different, like there's add, there are a bunch of other operations. But they're all really straightforward. You don't need to memorize all the operations to understand how LLVM works, right? The scary thing is that we are done giving you an understanding of LLVM's IR. The IR is that simple, okay? Instructions, operands, control flow, fee nodes to manage data flow. Question?
Yes, so both branches flow through entry. If I understand correctly. So how exactly does this work? Choose the right branch in the final.
So the question is, if you notice, all of the control flow paths through F go through entry. And so how is it that we know when to pick up this % entry value? So a fee node's operand is the immediate predecessor. Inherently, it's the immediate predecessor. So control has to flow directly from entry to end in order to take on the entry operand value. Does that answer your question? Fantastic. Thank you for the question. It's important to be brave and ask questions. Yes? How do you model iteration? That's a fantastic question. As it happens, we're going to spend a tremendous amount of time looking at that later in the talk, so I'm not going to deep dive on it. All right. So this is it. LLVM's IR is extremely simple. That's why I love LLVM. It's one of the really, really serious reasons why I like working on LLVM. It also means that LLVM is a fantastic model to use in your, a mental model to use because it's been distilled, right? It's minimal. It's not overly complicated. Okay, so where were we? We were looking at the IR for Hello World. If you think back, right, we're going to look at Hello World, or something even simpler than Hello World, and look at the IR for it. But this looks nothing like what I just showed you. So there are no fee nodes here, right? There's control flow, but there are no fee nodes. There's none of this SSA behavior. And there's a bunch of other stuff that we haven't even talked about, like we're allocating memory up here. There's all kinds of crazy stuff here. So what is this? The first thing you have to realize is that the optimizer's job is actually pretty big. The optimizer's job is not just making your code super fast, right? The optimizer's doing a lot of other stuff as well. So the first thing the optimizer has to do is clean up. Because one of the ways that we've gotten to the point where our front ends, we feel like we know how to build a front end, we know how to build a really high quality one, is that the optimizer handles a tremendous amount of cleanup from the front end. So the front end generates just obnoxiously bad code, but in specific patterns that it knows the optimizer can efficiently clean up. And so it can be very tricky to look at examples from LLVM IR. And so I've worked quite hard to make sure we don't spend too much time staring at cleanup code. But just to give you some examples, all right? So we start with this C code on the left, and we get this long amount of code here, like just very long amount of code here. And once we actually do this, the primary thing this is going to do is it's going to take these memory allocations. You're going to see that we have stores and loads from memory all through this code. It's going to try and take that, and it's going to try and put it into SSA form. So this SSA form with fee nodes modeling data flow is very complicated to form. So front ends typically don't do that. They actually just assume they have an unbounded amount of memory. They put everything into memory, right? They just use loads and stores everywhere, and we let very carefully written algorithms in the optimizer form this SSA representation, right? And that's actually really, really important to keeping things simple and separating concerns. So when you run the optimization pass that kind of forms SSA out of this, all of a sudden this turns into something that makes a lot more sense. Okay, and we can start to recognize the structural elements here that are showing up here. So for example, we have this error check here, right? That if we have argc does not equal 3, we return -1. And here we have a -1, right? And so this is corresponding to that -1. Okay, and you can start to see how this stuff becomes more like what we've been talking about. Make some sense? Have folks already noticed the first bug in my slide? Good. Yes, question?
The high node arguments were flipped there.
Yes, that is the first bug. Okay, step 2, canonicalization. So once we have simplified all of the code from the front end, we actually have a representation that seems like a reasonable way to represent your program. We now need to try and canonicalize it, because it turns out that there are quite a few different ways to write the same thing. For example, setting aside, horrible stylistic flaws that I have made, for very boring integers, right? There is no manifest difference between all of these snippets of code, right? Anyone, like these all do the same thing, fundamentally. And so we don't really want the optimizer to have to plan on optimizing each of these different patterns, right? And if you scale up to real code instead of this very trivial snippet, the number of different patterns becomes completely intractable. So a huge job of the optimizer, in many cases, the biggest job the optimizer has is actually trying to canonicalize all of these different ways of representing things into very rigid, predictable patterns. Okay, so if we have this, function, our little example we have here, right? We now have SSA form, but this isn't canonical. So if we canonicalize this, you may have missed that. Okay, so if we canonicalize this, something did change here. So we have not equal to 3 and a conditional branch at the very top. But not equal to and equal to are kind of just different variants of the same thing. We don't want to write all of the different variants. So we canonicalize this not equal to into equal. And we reverse the branch to keep the logic the same. And so in all of the LLVM optimizer, almost nothing looks for not equal to comparisons. We just don't have to handle them. Even though the IR supports it, the optimizer doesn't have to handle it. It gets to recognize a simpler, more canonical pattern set, right? And we just have a single piece of the compiler that goes and tries to rigorously form these patterns over and over and over again. It turns out that this is a tremendously important part of the compiler. Okay, and this is also something that LLVM is uncommonly good at, right? This is something that LLVM has pushed further than a lot of other compilers. And so, then there's another step of canonicalization. We've canonicalized this instruction, but there's also, the canonicalization of the actual control flow graph, because we have this, totally empty basic block here. All it does is go to another location. We don't need that, right? We don't want to recognize all possible control flow graphs with empty basic blocks in them, because that's not very well-bounded set. But we have a canonicalization for that as well, and so if you run that, it's going to remove, here I'll show it again, so we start from having if-then and end to removing if-then entirely, sinking the logic into the return. Make sense? This is just canonicalizing the representation. Okay, how are folks doing? Folks happy with LLVM so far? Excellent. Step 3. This is where things get important. Okay, so all of this stuff has basically, if we look at this code, right, we've basically spent a bunch of time figuring out how the compiler takes seemingly simple C code, right, or C++, but in this particular case C, and turns it into reasonably plausible internal representation, right? But we haven't actually done anything really exciting to optimize this, okay? And for C++ in particular, the exciting part of optimization comes when you hit the abstractions that C++ uses, right? All the abstractions that allow us to build massive software systems on top of C++, how do we collapse those to retain performance? I think this is actually what sets C++ aside from every other language I have ever worked with, is the ability to build abstractions which collapse, right? Which collapse to very efficient code. So this is where I'm going to spend most of the time kind of walking through the fundamental abstractions your programs are made of and how the optimizer models them. All right, folks happy with this so far? Questions before I move on? Excellent. So I'm going to claim there are 3 key abstractions to every piece of software in the world. And we can of course debate this forever, but that may not be useful. So the 3 key abstractions are, first and foremost, functions, calls, the call graph, that type of thing. Second, we have memory, right? Memory is a fundamental abstraction, right? Having loads and stores is very, very important. And the third are loops. Everyone buy my abstraction set? All right, so how do we handle these abstractions? How does the optimizer dig into these abstractions and extract the efficient code that you would have written if you were just paying no attention to scale or maintainability? First, we also need to talk about what other optimizations there are. Have you folks here taken an optimization class? Or in memory, a few people, right? You may remember lots of words about GVN and like constant propagation and other things, and I'm not going to talk about those. The reason I'm not going to talk about them is that they actually aren't that important, which kind of ruffles people the wrong way. So it turns out that a lot of the fundamental optimizations, they're important. You have to have them. I don't want to say that they're unimportant. If you don't have them, nothing else tends to work. But they're relatively straightforward. They're well-researched. You can go read a ton of academic papers and buy a textbook off the shelf. It'll tell you everything you ever wanted to know about it, probably a lot more. It also turns out that the advent of SSA form in optimizers obviated 80 to 90% of the fundamental optimizations. SSA form makes constant propagation trivial. It makes many other things straightforward, like tremendously straightforward. Data flow used to be a primary area of research in compilers and optimizations. And with SSA, data flow is straightforward, right? Local data flow is straightforward. So I'm not going to talk about these. I actually want to focus on this kind of less well-researched area of abstractions. So let's look at function calls and how we actually model function calls. So the optimization which collapses a function call that is unnecessary away is called inlining. You guys probably have heard this. There's even an inline keyword in C++. Please don't confuse yourself. The inline keyword in C++ has very, very, very little to do with optimization, possibly nothing to do with optimization. Inlining for optimization purposes is something very different, okay? And I want to be totally clear, this is the single most important optimization in any optimizing compiler, period. Inlining is the most important one. Most of your abstractions as programmers are going to be functions. Especially after the optimizer has run, the ones that are left are primarily functions, okay? It also is just about the hardest problem because it suffers from the Goldilocks problem, okay? Folks know the story of Goldilocks? A few people? Maybe this is just culturally lost on everyone in Germany. Sorry for that. The idea is that if you inline too much, you end up with software that looks like this, right? It's not too pretty, it's quite slow, it's not what you want. And so you know, you can inline too little, you don't collapse the abstractions. You inline too much, you get that scary thing. And so you have to find just the right amount of inlining, right? And that's really hard. This means that there's a lot of uncertainty. There's not this clear answer for inlining. So how do modern optimizers actually work with this? I'm going to describe LLVM's inliner here. This is one place where there's actually more divergence between compilers than you might imagine. LLVM's is somewhat novel. Okay, so first we need to imagine a call graph in order to imagine removing edges from a call graph. Okay, so this is my delightful call graph. I have a function A calls B calls C and D, C calls A. You'll note that there is a cycle here, okay? And D calls E, so on and so on and so on, right? Very straightforward graph. The very first thing we have to do in order to really effectively break apart this problem and decide which of these edges, right, which are calls, need to be removed to simplify the program, okay? And to figure that out, we need to kind of start analyzing this. The first thing we do is we break apart the cyclic components, okay? So we identify the strongly connected components of this graph, that is, all of the functions which participate in some indirect cycle. And so the blue ones here on the left are a strongly connected component. In the middle, we have the red ones, D, E, and F, a strongly connected component. And then at the end, we have G, H, and I, a strongly connected component. Once we partition things into strongly connected components, we can start to iteratively work through this using graph algorithms, okay? So the way the inliner analyzes functions is it's a mouthful. It's a bottom-up, SCC-based call graph walk, which is a whole lot of words. And I'm going to try, and instead of explaining these words, explain this with pictures. Okay. So the first thing that the inliner does is it starts at the leaves, because we have all the information we need to analyze the leaves, right? This connected component does not call any other functions, right? And so we can try and simplify this strongly connected component in isolation. We can see if, you know, G to H, H to I, or I to G needs to be simplified. They don't interact with anyone else. It's very, very nice. It's a very easy way to kind of isolate this stuff. Once we think that all of the functions in this SCC have been optimized, the inlining has taken place that we want, we've simplified it and collapsed all of the unnecessary abstractions, we can then kind of shift up the call graph, okay? Now we're looking at the next node. Now here we have a tricky problem because when we analyze E calls into G, another SCC. It's really important that we have already optimized G. Otherwise, when we consider the pair E and G, we're not going to have the right information, right? Maybe G is really trivial, and we don't know that because we haven't optimized it yet, right? And so this is why we do this kind of bottom-up approach, so that by the time we see a call edge, we've had a chance to optimize both the callee and the caller, right? We've had a chance both to optimize G and E. Okay? Now, once we do this, right, we optimize everything. In this SCC, within an SCC, we have far fewer options. Because it's cyclic, we simply have to pick an order, and we do pick an order. If we want to get really, really fancy, we will iterate a few times through that order to try and understand what's going on. But there's much less you can do within a cyclic component. And this is primarily trying to leverage the graph theory to break apart this problem. Okay. At the end, we continue down, we end up getting to the bottom, optimize that away. Okay. So how do we actually decide on the complexity of removing one of these abstractions, right? The reason we have abstractions in the first place is to break down a complex problem into smaller, simpler problems that we can connect, right? It's very, very useful. We don't want to remove all function calls in the program. That's not the end goal here. And so we want to try and have some criteria to evaluate where these abstractions are hurting the program's efficiency and where they're actually helping, where they're actually the right abstraction boundaries to have in the software. So we need to try and evaluate this complexity, and there are various ways we can do this. I'm just going to give you kind of the highest level idea of how this happens. The first thing we want to look for are cases where the call is actually adding nothing but an abstraction boundary, right? And this actually shows up all over the place. Wrappers, right? You've got a function G, you don't like the way its arguments are structured, so you write a function F that takes slightly different arguments, like swizzles them around, right, and then immediately dispatches to G. This is actually what most of your functions look like. Really, like most of the functions are really boring. They're just kind of lining things back up to hand it off to some other function. And this is what we're looking for. These are the abstractions we want to collapse in an optimizer, because these are useful abstractions to you, the programmer. They are not useful to the machine when it's executing. So we try and look for that. Now, sometimes, though, this is tricky. This can be really tricky to identify, because we might have something like this. Maybe I have my fancy sort. And just for the record, this is not a contrived example. If you look at your std sort implementation, especially the one in libc++, you'll see that it ends up looking something very much like this, where you test for various sizes, and based on different buckets of sizing, you pick different algorithms, right? Now, if I know something about the size of V for a particular call site, for example, if I happen to know that V is empty, well, then I really want to inline this function because it doesn't do anything, right? But if V isn't empty, maybe I don't want to inline this function, right? And now I have this contextual decision. That's why, again, we walk through the SCC from the bottom up, because we need to look both at the caller and the callee and try and use as much context as possible. Context is the key to very accurate complexity measurements for inlining. And so you have to have that context available. Now, one of the other things to think about is you have to make that context visible to the optimizer. And that's something we're going to come back to again and again here. Yes, question?
So that means that you may have to...
So the question is, doesn't that mean we'll have to go in and validate previous decisions? So it might. That's why we do this in this order. Okay? Because we want to inline all of the code in D before we go and look before we go and look at the B to D call, so that we have as much information as possible, we also want to optimize these three functions as much as possible to try and understand the context. And we still get it wrong, right? There are still cases where you actually have the information in B that this is going to be empty, but you're making the inlining decision out at G. And it's one of the hardest cases for the inliner. The inliner in LLVM still does not get this correct. We have a bunch of really complicated techniques that try to deal with this. We essentially try, so when we look at E to G, we will look at the call E to G, and if we see a particular indicator that the call from E to G might be one of the cases you've identified, we'll try and like defer it and put it on a queue to revisit that decision later. And then we'll go ahead down to B, and then we'll do some inlining, and then we'll say like, we have a queue of things to go and revisit, and we just did some optimization here. Let's go look at them again and see if we can make a better decision now. It doesn't always work. This is why it's hard. Okay. Excellent question, excellent question. So, as an example of that question, it's like I had a plant. As an example of how this actually happens all the time in the real world, and something that I want you all to think about the next time you write a variadic function. Variadic functions are the perfect tools for creating this scenario we just discussed. All right? If you have a variadic function, in a lot of cases, the initial call to the variadic function is going to have really interesting state. You're then going to have this massive recursive call, right? Because remember, this is a variadic thing. So each time we're popping off one element of the variadic parameter pack. And so if we have 20 arguments here initially, we have this 20 deep like recursive call. It's monstrous, right? It's terrible. And when we go and we pop all of this off, we may end up in the situation where we're trying to inline down at the leaves and we have no information and we can't make a good decision. And then at the very bottom of this, we'll see like, oh, actually, in this particular case, it's all zeros. Our bad, right? And this is actually the case that motivates a lot of the work I'm personally doing on LLVM's inliner, because we still do not do this correctly today. Question towards the back. So the question is, aren't there easy ways to handle this by I'm not sure what word you're using, but you can solve this by essentially going forward instead of backwards. Tail recursion, sure. Tail recursion is one way to solve it. In a lot of cases, tail recursion doesn't apply. The case I looked at. No, so the actual real-world case with where this came up was not tail. And in fact, it can't be because the number of arguments are always different. Right? And so it's actually very rare that tail recursion fires here, unfortunately. There is a good way to solve this, and tail recursion is kind of similar. If you were to redesign the inliner to work from the top down, right, then you would start off with that call that had all zeros, right? And then you would be able to propagate it through every level of this recursive call, and everything would simplify away, and it would be beautiful. And that's actually how GCC's inliner works. This is one of the biggest differences between GCC and LLVM. There are strengths of both approaches, there are weaknesses of both approaches. And actually, both of them try to do hybrids of their core approach and the other approach because of these patterns. Any other questions about this? All right. So with that, let's look at the second abstraction, memory. Okay, still with me? Yes? So there are two elements to this question. The question is, in essence, is this a binary decision? And it is a binary decision, but we try to, we have to choose to inline or not to inline in the simplest case. But we try to make that binary decision in a fine-grained way. So we make it per edge, not per function. right? So that handles the majority of cases. It doesn't have to be a binary decision, though. There are all kinds of very complex things, partial inlining, partial specialization. There's a world of tricky optimization here. But I'm mostly trying to give you guys a framework to think about it and not trying to give you the entire optimizer. Okay. So, memory. You guys probably familiar with memory, pointers and such, right? It's kind of important. It's very fundamental. I'm not going to spend as much time with this because I think actually people already have the right intuition about memory. The primary thing I do want to point out is kind of this key thing about forming SSA, because when we form SSA, we're actually taking things out of memory, right? We're actually removing a memory abstraction. Now, in most cases when we're putting things in SSA, that's not a real abstraction. The programmer didn't allocate themselves to memory and put data into it. In most cases, it's just that the front end did it for you. But it actually shows the core principles that we use for all kind of memory optimization. So if you look at this, right, we have allocated memory on the left-hand side, right? This alaka shockingly allocates memory. We then, compute something and we store it into that memory. We then have control flow. On one path of that control flow, we compute something else and we store that into the memory. And at the end, we load it from memory. Really straightforward, right? And if this weren't on the stack, if it weren't a local variable, this would actually be an interesting problem that would come up, right? Where you have heap allocated memory, you do conditional stores into it, and the optimizer wants to figure it out. So the way that the optimizer tries to figure this out is a few different things. The primary thing it's going to try and do is model what the value of this memory is throughout the control flow graph and identify merge points, right? So when we first see memory get allocated, we know that the value is nothing, right? It holds nothing, right? We then see a store to it, and so at the end of entry, we know that the memory holds this value, this %C, right? And then if we look at the two paths, and then, right, we see that the memory now holds this new value, %D. When we reach end, we actually see the merge point, and we add the phi node. This, it seems too simple to be true, but really that's all the compiler is doing, is it's just tracing where the values are in the control flow graph, what values are available in the memory at each point, and identifying merge points in order to promote them from memory to this very nice, easily analyzed SSA form. And you can actually take the same core technique and apply it to all manner of other things. I even have a slide for this. Yes. So, but the other thing that's kind of frustrating is, this is an integer, which is kind of boring, not too exciting. Sometimes you have complex memory. And this gets to the real challenge of memory as an abstraction, is when it's not just a single, integer, but you have some complex structure. So, sorry, we're getting a little bit more code here. So we're going to have a structure type, which has 3 integers in it, okay? And we're going to allocate a complete structure, okay, for our memory. We now have to deal with pointer arithmetic and indexing. So LLVM actually has a special instruction called getElementPointer, which handles all of the pointer arithmetic, okay? And the pointer arithmetic looks into this memory, and it actually looks at the type %s to understand how the memory is partitioned into values. We index it to get the address of the first element, we index it to get the address of the second and the third, right? And now we do loads and stores to them. The interesting thing is, we now have a much more complicated problem to solve. Okay? We don't have one memory location that takes on different values in the control flow graph. We have a large memory location, and different pieces of it are taking on different values at different points in the control flow graph, right? And some of it's changing, but some of it isn't. Address 0 isn't changing in the control flow graph here, even though it's the same chunk of memory. And we have to have some way of reasoning about this. The classic way that the compiler tries to reason about this is by partitioning, right? It just wants to look at the memory, find every indexing, right? All this pointer arithmetic, find how we move into the memory, how we load and store into the memory, and use that to deduce a partitioning of the memory so that we can separate out all of the constituent pieces, right? And this lets us take a structure and turn it into individual variables. Once we do that, we're back to the simple problem, right? We just track that location, keep track of what's available where, and we can promote them to registers and get rid of the memory entirely. And so we want to use this partitioning technique here. And with just partitioning, right, we're able to get rid of all of the memory accesses here. Making some sense? Now, sometimes we aren't lucky, and we can't partition things. The full scope of memory optimization primarily boils down to finding some other way to isolate a particular location in memory and doing a partial job of forming these SSA values, right? We just want to try and find some way of isolating these values in memory. Partitioning is the easiest and overwhelmingly the most common. But there are a bunch of other techniques in the optimizer to try and isolate these locations of memory, track them through the control flow graph, reason about what their actual values are. Making sense? Yes?
In that example, it's kind of the memory allocation happens local within a function.
Yes.
It returns an integer.
Yes.
But if you allocate memory and it gets returned, you cannot eliminate that memory calls, right?
Yes. So if we were to allocate the memory, the question is, if we allocate the memory, we can't eliminate all of these stores. But what we can do is we can model the entire function body without the memory. And then when we leave the function, we can set up the memory so that it has the right observed values, right? And this gets down to trying to partially pull things into the registers, right? To the extent we're able to. Other questions? Yes?
It seems to me that the front end and the optimizer really disagree on what the right level of abstraction is. So to me, it seems that the front end really goes too deep down in the abstraction, and the optimizer tries to raise the abstraction later.
So
Is that really what you think is the best
So-
answer to the design?
let's see if I understand your comment. The comment is that it seems like the front end is operating at this very, very high level of abstraction that the optimizer does not want to operate at. And the optimizer is having to go and undo all of these poor abstractions. So the key thing to realize here is that it's not the front end that's actually operating at that level of abstraction, it's the programmer. The front end doesn't care about using individual variables versus structures. Doesn't care about using one function versus 10 functions. But programmers do, because that's how they think about things, right? Like, we can't keep track of all of the local variables necessary for all the state of our program. But we can build types that package together a collection of the state necessary for some piece of it, collection of the functionality in functions for some piece of it, set that aside, and now deal with it in a simpler way. The abstractions are critical to programmers, and the choice of the abstractions comes from the programming languages. And those are the abstractions the optimizer's digging through. Some of my slide examples are less interesting, but that's because they have to fit more than anything else. Other questions? Okay. So the third abstraction that I wanted to talk about are loops. And a lot of people, myself included, in a past life, are like, who cares about loops? We don't need to deal with loops, right? Because because if you really cared about loops, come on, please. You're not going to write C++ code, right? Anybody here write Fortran? Good, I'm glad there are at least some people who I'm poking fun at here. Fortran is a beautiful language. If you haven't written in it, it really is a beautiful language. It's totally different from how we think about programming language today. I find it fascinating. I'm not being sarcastic. I'm not being facetious at all. It's actually an interesting language when you look at how it works. I don't think it's the right language for me personally, for most software, but that doesn't make it a bad language. It was perfect for what it was designed for. And we've got millions and millions of lines of Fortran code that I don't think we will ever get rid of, because that problem and the programming language and the code evolved together into a pretty near perfect solution, right? And if you look at the kind of scientific industry, you'll see a lot of this stuff. But that being said, we do actually have a lot of math and loops in C++ code as well, and we really need to be able to talk about them and reason about them. Is anyone here, how many people have heard of eigen? Excellent. So I don't particularly like eigen. But I admire it. Eigen is an amazing accomplishment. If you haven't checked it out, you should. It's a linear algebra library. It's an incredibly powerful C++ template-driven linear algebra library that does a tremendous amount of domain-specific mathematical optimization through template metaprogramming, essentially. And it does a really tremendous job of it. It makes linear algebra both fast and relatively straightforward to write. Unfortunately, it makes the error messages from the compiler relatively not straightforward to understand. But you know, that's somewhat the compiler's fault, so I can't give them all the blame. But like, loops are actually important to C++, and so I want to try and give you guys a framework for loops as well. But loops are going to be a little bit more complicated to talk about because this is actually where I think the largest amount of research has gone into how to optimize, right? We do more to optimize loops than almost anything else, which actually makes a certain amount of sense. A loop is probably where your program is spending most of its time. I hope. Right? Like, if it's not, if it's spending its time in any of these other abstractions, we've done something terribly, 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 terribly wrong. So I'd like to try and talk about loops. I'd like to talk about this very advanced loop. Okay, this is some excellent, excellent code here, right? We have taken a vector of integers, and we have summed them in the silliest way possible. So, very simple loop. This should be a good framework for talking about how loops are optimized, right? Here is the LLVM IR optimized for this loop. There's a lot. LLVM tried very hard to optimize this loop. So I actually, you know, when I started off on this, it was a little frustrating because I wasn't sure how to distill this into useful examples. I had to do a bit of work. So these examples are going to be slightly contrived to avoid this, but I'm going to try and stick with this idea, right? So this is my loop, right? We'll get to what all of this is doing. So let's look at this in a simpler form. Okay, so I've kind of done all of the cleanup, all of the canonicalization, all of the inlining and everything else here, and this is actually what you end up with if you do all of the other optimizations we've talked about so far. If you optimize everything except for loops, this is what comes out of the optimizer. Bit of work to get this. I've also renamed things to be easier on your eyes, okay? So we can kind of follow what's going on here. I mean, it doesn't precisely fit, but I think you guys can follow what's going on here, right? We have, you know, there's some big aggregate vector type, right? And we have to index it to find the begin address, and we load the begin pointer out of it, right? We load the end pointer out of it because it's a struct and it was passed in by reference, and so it's in memory, right? Once we have the begin and end pointer, right, we go to the loop. In the loop, right, we start with begin and a sum of 0. Right? We compare to see if we have already reached the end, and if we have already reached the end, we go to exit. Right? If we have not reached the end, then we need to accumulate things. So we take the pointer, the begin pointer, and load it, load the integer out of it. We add it. We move that pointer one integer forward, and we go around the loop. Now, I did not craft this. Right? Like, literally, I renamed these things, and I deleted line noise. This is actually what the optimizer does for a really complex piece of C++ code. Because, like, there's a lot of stuff going on in this C++ code, right? I've got a vector container. This auto is calling functions, right? It's creating a reference and variables, and then this binding thing. Like, this is doing a tremendous amount of work under the hood. But the optimizer actually deletes all of that and turns it into this very simple numerical loop. I think this is beautiful. But it's not very fast. And so let's see what we can do about this. So the first thing you have to realize is that, you know, just like we have these other steps in the rest of the optimizer for loops, we actually have the same steps in minutia, right? We have to canonicalize, we have to clean up and canonicalize the loops, just like we have to do everything else. Because loops are a truly special form of control flow. It's a really fundamental abstraction. We want to try and form really recognizable loops. So the first thing that LLVM does is it kind of canonicalizes the loop into this. I can't show these side by side, but I'm going to try and explain what's changed here. The first thing that LLVM has done is it's created what's called a loop preheader. Okay? Now, what a loop preheader is it's a distinct basic block whose only job is to enter the loop. Right? That's what this empty basic block is. It's really boring. It also has created a loop exit block, okay? And I've called it loop exit to make it very clear. And this is, the only purpose of this is to be the single basic block which the loop exits into, right? With no other predecessors, okay? We also have a weird looking phi node here if anyone is like really thinking about SSA form. So let's go back to SSA form. The idea is that when we have two different values in the control flow graph, and control flows merge at some point and we select between them based on where we came from, we have a phi node to model that selection. Well, here we have a phi node with only one input. Okay? There's only one predecessor of loop exit, and that's loop. All right, and so what we're actually doing here is we're adding a synthetic phi node, which helps us model the fact that this x.next value lives out of the loop. Okay? Even though there's only one predecessor, in many cases, we create a special phi node just to model, this value lives out of the loop. You can also kind of conceptually think about it as modeling, this is a value which we don't merge, but we select the last iteration's value for. Okay? Turns out to be really, really useful. We're gonna see some of why. The last thing that you'll notice here is that this has all been kind of switched around. So before, we had two basic blocks in the loop. Right? We had the start of the loop, which involved checking the condition to see when we were done, and we actually had the latch, which I'm calling the latch, which actually does the arithmetic. Here we only have a single basic block. What we've done is we've actually taken the condition, right, pulled it outside of the loop entirely into a precondition, okay, because that precondition has a special behavior of not looping. And we've now been able to kind of rotate all of the logic of this loop around so that every time through the loop, we actually do the accumulation, right? And this simplifies how we think of the loop. And that's why we had to have a special loop exit block in order to have an exit block that doesn't have some other predecessor, because the actual function exit may have never gone into the loop at all, right? It may come directly from entry with the value of 0, because we did not satisfy the precondition. Make sense? So this is called, in LLVM's terms, loop canonical form, right? And we try to keep loops looking like this because it makes everything else we're going to do much easier. Okay. Questions about the kind of canonicalization of loops? I'm fairly happy with how we're doing this. Okay. So this is subtle, sorry. So at the very top, we're going to change something. Here we're getting the end value out of the vector. So in order to talk about how we actually optimize and simplify loops, I'm going to hypothesize what if some other optimization had fired? What if inlining or something else had collapsed some part of this code to something that allowed the optimizer to simplify the structure from a loop? The first example I'm going to give is what if this end pointer isn't dynamic? We don't load it out of raw memory. What if we know where we are going to end? So here we have begin, right? We load begin just like normal, but we compute end as 4 elements past begin. Exactly 4. Okay? So now there's an opportunity for the optimizer to go and improve this code because we know how many trips around the loop we're going to make. 4, right? So how does the optimizer actually do this? This is the first really fundamental loop optimization when we were looking at the abstractions that we're trying to break through. And this is to take something that is a loop, like this, but that does not need to be a loop, and make it not a loop, or unroll it into straight line code. So here we have constant 4, and if we run loop unrolling over this, you will get a loop basic block which just directly exits. Okay? 4 copies. And by the way, you can actually try this. I can try and put some of this code up. This code I actually tested because the loops are big enough code, I didn't trust myself anymore. And so you literally can take this IR and you run loop unroll in LLVM over it, and it just unrolls the loop. It's beautiful. Okay? So we have taken an abstraction, which the programmer wrote, which is a loop with a constant trip count, and we have taken it out of the program to make it simpler. It's now easier for us to reason about this program, dramatically easier to reason about this program. So the takeaway you should have here is that if anyone ever tells you to not write a for loop with a constant count in it, because now the optimizer is going to have to work harder, they're wrong. Okay? If that's easier for you to write and read, write the loop. Totally fine. Optimizers are amazingly good at unrolling loops with constant trips. Okay. So we've unrolled a loop, but most loops that we care about, especially loops that run for a long time, don't have a constant trip count, because that's kind of weird, right? Usually they have a dynamic trip count. So let's look at some other optimizations. So this is the same loop, but I've inserted some code in the middle, all right? So there's this extra code going on here, this %first. Okay, %first is new here. All we're doing is we're actually loading the first element. Okay, we've already had the precondition outside. We always have at least one element in the loop, but we always load the first element. And the reason we always load the first element is that as soon as we finish the loop, we actually are going to use it. We're going to scale the result by the first element. I don't know why this is useful, but let's say it is. Okay, but this is actually a bad abstraction because I have code inside of this loop, this load, which is completely irrelevant to the loop. We're going to load this first element every single time we go around the loop. There's no point in that, right? So the second kind of really fundamental thing that we do to try and optimize the loop abstraction boundaries is to move code out of loops. So we want to move this load out of a loop. The question is, how do you do that? So this is where all of this canonicalization pays off. We know about the loop invariant things which survive a loop because we have a Keynote for it right here. So we can look at all the things that come out of a loop. We can see which ones are totally, invariant. They don't change as the loop runs. We don't need to do it inside the loop, and we can sync first into this Keynote, right? And so now we load the first because this was loop invariant, and so we move it to first at the loop end, right? We load it there. Now we only load once. We get the exact same behavior. Make sense? This is a super trivial example of moving code out of loops. I know it's kind of contrived, but like nothing else would ever fit up here. This comes up all the time because you have functions you're calling in the loops, and these functions often are doing random things that have nothing to do with what the loop is doing. For example, if you're calling .size on a vector inside of a loop that does not modify the vector, right? That .size is doing a lot of work which has nothing to do with your loop, right? And this is the technique the compiler uses to move all of it out of the loop so that you don't have to. We don't want programmers to have to sit around and remember to cache all of the intermediate values that they might want to use from their loop body in local variables, right? That's a total waste of time. Now, sometimes it's hard, but like to the extent possible, the compiler is going to try and handle this for you. It'll actually handle even more complex cases, which I wanted to fit into a slide, and I tried a bunch, and I couldn't. This is a invariant operation in a loop. What happens when you have an invariant control flow in a loop, right? What if this wasn't a single basic block, but actually had a diamond, like divergent control paths? And the condition is actually what is invariant, okay? For this, just moving the condition out of the loop isn't the interesting thing. What you actually want to do is split the loop in two, right? One for one side of the condition and one for the other. And there's a whole class of optimizations around that. You can think of them as really a generalization of invariant code motion to also do specialization of loops. Okay. So the last thing I want to talk about is where probably most of the performance comes from. All of these others are essentially trying to make loops smaller, simpler, have fewer loops, right? Have fewer instructions in the loop and have them do less work wherever possible. But we then want to take this abstract loop that you have written and turn it into something that's very efficient. This usually means not doing a single thing on each execution. We want to kind of, use all of the resources of your very large processor to do things in parallel, to vectorize things, to really get the most out of the processor. And interestingly, almost all of the techniques for this fall into a single core idea, which I'm going to try and show you. And the way I showed you is I've put this weird metadata inside of my code, which will actually tell LLVM's vectorizer to do the very most boring and simple version of vectorization. It's not actually vectorization at all. It's just going to widen and interleave the loop so that we do 2 iterations instead of 1 at the same time, right? If you have a large out-of-order execution processor, right, it can often pipeline many things. By doing 2 iterations at the same time, you can often expose instruction-level parallelism, get significant performance. Vectorization is essentially a fixed form of this exact technique. Okay, and so when we take this loop and we kind of widen it and interleave it, we get this monstrosity, which also doesn't really fit. But I'll try and walk you through it. So we had a pre-header, right? Remember how important it was that we had pre-headers and exit blocks. They allow us to edit the loop in these very precise ways. So before we choose to loop, we're going to do a complex test. All of this stuff is trying to make sure that we have at least 2 iterations on the loop, right? Because if we're going to do 2 at a time, we can't do that when we only have 1 iteration. So we have to do a bunch of legality checks, okay? And there's this scalar preheader, which is kind of the fallback loop. We've preserved the original loop in a fallback location. And so if we don't have enough iterations, then we fail this test, right? And we go to the fallback loop. Then we actually have to do the test, and we generate some really silly code to do this test. This is a frustrating part of LLVM, but it doesn't really matter. What we're actually doing is we're setting all of the information up in order to do this widen thing. Now we have this vector preheader, right, which just jumps to the vector body, and let's look at the vector body. You can kind of scroll up here. Okay, so now we've kind of vectorized this loop, but it's really easy to see what we've done. Okay, we've taken all this stuff, and we now have 2 integers that we're keeping track of as we go along, right? We're indexing, we're adding more, we're doing 2 loads, 2 additions, right? We're summing them, and we're still keeping this accumulation going, but we're doing 2 at a time, right? And this is the entire loop, right? We've kept that loop structure. It's just widened to do 2 operations. And you can imagine doing any number of operations here. You can imagine using the vector unit. You can imagine doing all kinds of things. And they all take the same formulation, right? We check that it's valid, right? We then widen the body of the code. Once we run out of what's valid, right, we then fall down, and this middle bit kind of bridges to the scalar fallback. And the scalar fallback is the original loop. It's exactly like the original loop. And this way we can handle any kind of odd bits left over. Okay? And this is how vectorization works. This is how pipelining, like software pipelining works. This is how all of the really cool optimizations work. And these then scale from very simple to very, very complex operations on loops, right? If you look at, like if you ever want to look into more of this, look up the project called Poly, which does just amazing restructuring of your loop to try and achieve these kinds of results. Okay, questions about loops? Or is everyone just like, I have no idea what you're talking about anymore? No questions about loops? Yes, excellent.
Do you have to consider memory alignment for making the parallel loops?
The question is, do I have to consider memory alignment? Absolutely. I mean, in this case, we don't, because we're actually just doing more loads at a time, and so they have the same alignment before and after. But in realistic cases, we have to check for alignment, we have to check for, usually we're not just loading from a single buffer of memory, usually there are more memory operations, we have to make sure they don't conflict, It's actually valid to interleave the different iterations of the loop. There's a tremendous number of validity checks you have to do. This is about the simplest form you can get. And it still took 2 slides. Yes?
Question about unrolling.
Yes.
Rather simple. How do you decide when you stop unrolling? I mean, how many loops you unroll and how many you don't unroll?
So the question is, how do you decide when to stop unrolling? So there are really 2 different things to talk about here. The unrolling that I mentioned is the removal of a loop and replacing it with straight line code. And when you're going to completely unroll a loop into straight line code, you have a cost metric, but it's a little bit easier. What you're really looking at is you can look at how big the straight line code will be, how big the loop will be, and try and make some trade-off on how much simpler the straight line code is than the looping code and how much bigger it is, because you don't want to just make the binary enormous. It's a fairly easy trade-off function, but it's a pure heuristic. There's no principled aspect to it. Now, there's a separate technique, which is unrolling, but not fully. And I'm showing one form of that here, which is widening and interleaving. But you might, instead of interleaving the operations, actually just pack multiple iterations into a single basic block. They're both valid ways to do unrolling, and we often call the latter one runtime unrolling. Yes, and it has to have a cost metric much the same as this does, because there we're not actually simplifying the core abstraction. We're taking a simple core abstraction and actually making it more complicated in order to make it more efficient on a particular machine. And so we have to look at the particular machine to understand what is efficient on that machine, right? And it's very much a machine-driven decision, right? Whereas the other things I've presented for loops are not as machine-specific. They're very generic ways to simplify the abstractions. At the very back. The very, very back. You're good. Yes, you.
You have an example where you replace multiple loads by one and move it out of the loop, so that can change the behavior of the code. You have a concurrence. So how does that?
So the observation is that I had an example, I'll try and put it on the screen, here, where I have a load inside the loop, which will happen multiple times, and we sync it out of the loop. And the question is this could change the behavior, in theory. And the observation is that it actually can't change the observable behavior. So we know what other instructions are in this loop. And we know that none of them are modifying memory.
You're assuming that you have only one thread.
We're not actually assuming, so the comment is that we're assuming there's only one thread. We're not assuming that. So C++ and LLVM as well give us these really wonderful guarantees that if you're going to actually modify memory, like read, like even access memory from multiple threads, you have to use atomics. And so this is a non-atomic load. Because it's a non-atomic load, we know that there cannot be another thread modifying that memory. And this is a very important thing. We model atomic operations in LLVM directly from the C++ memory model by mapping them into LLVM's memory model, and we preserve this distinction. Because otherwise, yeah, we would have a lot of trouble determining whether there was synchronization. And this does actually rely on your code being correct and not having undefined behavior according to the C++ memory model.
So this all assumes like the data race to be
Specifically, this is legal because if this changed your behavior of your code would have a data race and would have no defined behavior at all.
How does it apply to standard algorithms?
So the question is, how does this apply to standard algorithms? Well, I wrote a range-based for loop, but I could have written for each, and it would have done the same thing. So standard algorithms tend to be loops inside of functions. So if we can inline the function away, we get back to the loop. And if we don't inline the function away, then this loop that we're looking at will be inside the algorithm. And this might be what std sum looks exactly like, for the record. Yes?
So with the techniques that you're using now to kind of get to this canonical form and then optimize from the canonical form, do you find that if someone tries to misguidedly sort of pre-optimize a loop by manually unrolling it in code, that it actually clears the pitch for the compiler to do?
Yeah, so the question is, if the user were to manually unroll and try to do vectorization or other things to their code by hand, will this impair the compiler's ability to kind of analyze the loop? And the answer is absolutely yes. Now, that doesn't mean it's always a bad thing. But this is exactly the point of this talk. When you go and manually unroll your loop or vectorize it or do something else to it, you need to understand the trade-off you're making. Yes, you're going to make the execution faster, perhaps. Your compiler may not have a very good vectorizer. LLVMs isn't the best vectorizer in the world. Maybe you need to do it by hand. But when you do that, you're sacrificing something else, right? Now, if that loop is used in a different context, where there's a fundamental simplification to the loop that you would like the compiler to do, it may not be able to. If there's a different context where a different pattern is optimal, the compiler is not going to be able to discover that and do it for you. And so I really want people to be not afraid of doing manual optimizations. I want them to be aware of the trade-off they're making when they do them, right? Because I think people tend to not think about that. They're like, well, a loop's a loop. It's faster this way. I'll rewrite it this way. But faster may not be what matters, right? It's a really, really good point. Other questions? Yes?
Do you consider platform on which you are optimizing, for example, the vectorization, because some of the platforms have some vectorization support with directly into, some of them don't have. Do you consider it?
Yes. So the question is, do we consider the underlying platform that we're optimizing for when doing vectorization, for example? And yes, I tried to mention that in another question. The vectorization, widening, any of the things which are not removing a loop abstraction or removing code from a loop abstraction, right, are fundamentally tied to what is the most efficient way to loop on a particular machine. And it's very contingent on the machine. And we have a ton of heuristics to try and look at the machine we're targeting and what its capabilities are and what the loop is doing and try and find the best fit. It's a very complex problem. Yes?
It looks to me that at each optimization pass you're losing some kind of information because you're always transforming the code. You could also, you're of course holding some information for loops, for instance, because you could see them just as a go-to label with a branch in this case and an increment instruction, but you're still losing some context. So the question is, how much is the order in which you perform the various optimizations important?
Okay, so there's both a comment and a question here. I'm going to kind of reverse them because I want to talk about your comment a bit. So the question is, how important is it the order in which we do these optimizations? And the kind of trivial answer is incredibly important. It's actually if you know there are 3 hard problems in computer science, right? Right? If you're asked a compiler engineer or a compiler optimizer engineer what the really hard problems in compiler optimization are, one of them will be called phase ordering, which is a really fancy way of saying we have no idea in what order to do all of these things. Right? We have guesses at best. But your comment actually gets to why this is hard. So the comment is about are we losing information here? And I want to go backwards a bit. Okay, so the key thing to look at is this transformation, because this typifies most of the transformations we do. This is a canonicalization. So we start with this loop structure, and we change it from this to this. This loses no information, right? It's information preserving. And it turns out that a bunch of these things are the same way. So when we do this, we're clearly just restructuring. But if we were to have a constant, right, and we were to unroll it, we also haven't lost any information, right? We had a constant before. We unroll it. We still know how many times we're loading, right? We haven't lost that. If anything, we've gained information because now we know that a loop isn't necessary for this logic, okay? And so, then we have moving this code around. We have a load in the middle of it. When we sync that load out, we haven't lost information, right? We've actually made it easier to discover that some of these operations are not dependent on the loop. And so there's a lot of these optimizations that are really carefully trying to preserve information, right? And that's important. The LLVM optimizer actually partitions all of the phases that it operates in order to address phase ordering problems into canonicalization phases, which it tries to do first, followed by optimization phases. Because once we start optimizing for a particular architecture, right, once we take something, simple like this and turn it into this massive pile of goo, we actually are losing information. We're not losing information in a theoretical sense, right? Like it's still there, but we're losing the ability to find the information. But there's one fallacy that really comes up a lot, and you kind of hinted at it, but I want to call it out here. A lot of people think that this arbitrary go-to label kind of control flow graph loses information. And this is actually a common theory, but there are really great algorithms that take an arbitrary control flow graph and extract a precise loop nest structure from it. And we know how to do this. This is relatively recent in compilers. 30 years ago, we did not know how to do this, and this was a big concern. And losing the loop nest structure was a big problem. This is actually why Fortran is actually a beautiful language, because Fortran was specifically designed to preserve the structural information about how your code accesses memory so that the optimizer doesn't have to recompute it. And something we've kind of discovered in the last few decades is that we can, in almost all cases, recompute it. The control flow we're really good at. We're really good at deducing loop structures. We're not as good at figuring out how you access memory, but we're getting better at that. That's where most of the research is currently going on. Did that answer your questions? Yes. So the question is, in both inlining and unrolling, we're essentially taking an abstraction that programmers tend to put in their source code and removing it to make efficient code. But what happens when the abstraction that we actually need isn't in the source code and we need to form it? And that's a perfectly legitimate set of optimizations. Compilers are actually really bad at this at the moment. I don't know why. Other than, I know why for LLVM. For LLVM, it's an engineering historical artifact. I don't know why all of the other compilers seem to also have struggled with this as well. But yes, outlining is a really important optimization. That one is done by most compilers. LLVM is actually really bad at that. Loop re-rolling and loop formation is also a really important optimization. And I don't know why it isn't more widely used. I wish it were. But there are only so many hours in the day. Yes? So the question is, the compiler is having to do a lot of work in order to do things like widening and other kind of very advanced optimizations, where it's trying to check whether your loop satisfies some set of constraints that you may know a priori. And can you tell the compiler about that? In some compilers you can, in other compilers you can't. It's actually something we're trying to get more into the language. We've just added a lot of really great infrastructure to LLVM to support this, and we're working on kind of the first cut at supporting this in C++ with aliasing information being available in the language right now. Michael Wong and some other folks are working on a paper to propose aliasing annotations. And I'm really hopeful if that goes well, we'll get other annotation syntaxes in the standard so that you can get kind of portable ability to specify the invariants of your program. Right now, my suggestion is actually to use things like assert, because some implementations have been really clever, and they will extract these from asserts in your code. So the comment is that compilers seem to be really bad at unrolling loops which have complex control flow within them. Is that a good way of putting it? Very common, like early exits and other things, but not simple basic blocks. And the answer is yes, that as soon as you add more control flow, right, you're going to make this harder. But I think a lot of this is actually just engineering shortfallings. I can speak directly for LLVM. We're currently trying to turn on much more powerful loop unrolling because we have these engineering shortfalls. And I think you're going to see substantial improvements there. I don't think there's a theoretical limitation there. I don't think that should factor into your kind of mental model of how this works. I just think you should file bugs against the compilers until they get it right. Maybe I'm just mean to the compiler implementers. Yes? So the question is, right, especially for standard algorithms, we have a bunch of different ways of writing roughly functionally equivalent loops, right? You can use integer-based indices, you can use iterators. There's some concern, like, will the optimizer handle all of them equally well? I think that most optimizers will handle them fairly well. So keep in mind, right, like, one of the things that I really loved about this example is the fact that, if I get back to this code, right, well, and even the simpler one, right, this code came out of a real, like, big loop with a standard container and iterators involved, right? There were vector iterators and everything in here. No problem, right? We distilled it all the way down to pointers and indexing, right? If you use an integer index, we should get to the same place. This is about canonicalization, right? There are a bunch of ways of writing these loops. We have to canonicalize them to a single pattern, and then we should be able to optimize them well. I'm sure there are places that we're missing it, right? But I don't think that this is what the job of the compiler should be, to allow you to write the loop in the way that works with your abstractions. If you have iterators, use iterators. If you have indices, use indices, right? You shouldn't be spending your time on that. The compiler should canonicalize it. Question up here. So the observation is that the hints you might want to give about invariance of a loop or probabilistic, likely patterns in a loop are things that profile-guided optimization might be able to provide. Absolutely. Profile-guided optimization can provide tremendous amounts of hints of that form. Profile-guided optimization can't provide invariance, though, right? Because you never know whether you just haven't gotten that one workload which will cause that other path to be taken. So you can get very good probabilistic information from profiles, but you can't get a true invariance of the software. That's the gap. And I think the right place to bridge that gap is with annotations. Towards the back?
So the right version?
The question is, could we have some diagnostic to try and tell you that your loop is not getting canonicalized and optimized in the right way? I don't know how to implement that very effectively. I could implement a kind of bad form of that very easily. I don't know what a good one would be. And in particular, I think to make that a very good thing would be about the same as teaching the compiler how to do the canonicalization, which is kind of an unfortunate, where do we spend our time? It certainly would be useful. I'll argue, though, that while you don't have the best diagnostic, you already have a diagnostic about this. Because if you care about the performance of this loop, you have a benchmark for it. And if you have a benchmark for it, you should notice when the compiler fails to optimize it very effectively. It's not a great way to learn about it, but you always have ground truth you can go back to. I've seen a hand in the middle here. Yes?
Question about vectorizations, right? Because I saw you were interleaving the same instruction twice.
This really was just an example. I'm not advocating that you do that to your code, right? Here?
What thing anywhere is ensuring that these instructions are going to be on the different issue lines?
So the question is, when we do this interleaving, what ensures that the instructions are going to be issued in parallel on the particular processor? Again, the selection of what to do here is done with tremendous amounts of machine awareness. And so when we tell the optimizer, you should interleave, it's because we know that the processor can have instruction-level parallelism. We also know that the form of this code will be recognized in the backend and generated into particular machine code that we also know the processor will then see and correctly form ILP from. Now, we can have mistakes and bugs anywhere in that stack, but that's the idea, right? That's part of the heuristics. Yes, on the aisle.
Is anything which the front end generates already, or will it also be optimized if there is no compiler optimization that you will compile? So in debug mode, is there anything done?
So the question is there anything done with the code coming out of the front end to optimize it if you completely remove the optimizer? The answer is no. I mean, to an extent. The only real thing that the front end does to try and do some optimization is it will try to not emit dead code. It's not much use. The goal here is a separation of concerns. Now, what we should be doing, and we're not right now in LLVM, GCC is actually doing a really good job of this, is we should be working with our optimizer to run some of the optimizer even when you're doing debugging, so that you actually get reasonable performance and reasonable debuggability. GCC, I actually am really impressed by some of the work they're doing here. I think LLVM has a lot of work they need to do here. A bunch of hands over here. Yes?
A lot of this depends on your ability to inline the function or the function calls inside it.
Yes. Yes. All of this is just focused on loop optimization.
How about cross-module optimization? You don't have access to the code.
Okay. I thought you were going to be my excellent plan to move us into the next section of the talk. So I'm going to mishear your question. I'll come back to your actual question. so what, like, how do we actually handle the case where we have loops and function calls all intermingled, or you know, even something simpler like function calls and memory accesses intermingled? Right? What happens when these different abstractions are combined? You were so close. I do appreciate it. So when these things are combined is actually when the optimizer struggles the most. Okay? Every time you take an abstraction boundary that you want the compiler to kind of reason about at a high level and potentially remove, right, or transform in a very intelligent way, and you commingle it with another abstraction boundary, you are making the problem the optimizer must solve fundamentally harder. Okay? Now, I have this really kind of seemingly silly example that I like to use. Okay? So as the classic example, right, you have this code, right? Two ways of writing code. You have a function that accepts two arguments, right? And you have this really annoying output parameter. What we have done here is we've taken two totally different abstraction boundaries and we've commingled them, because now analyzing G, right, and understanding whether it makes sense to inline G requires reasoning about memory, because we have this output parameter. It's not functional, it's not pure, it's not, like, it has all of these properties that are harder to reason about. And it can be even worse than this. So my personal least favorite example of this, and like for the record, like, you have this, the way to write this code is to use return by value, right? Take memory out of this, right? At any point where you can reduce the number of abstractions that are mixed, do so. Now, the place where I really get bugged by this is here. Because a lot of people look at this and they're like, what? There's no memory here. Anyone see the memory here? This like, it seems so trivial. This actually shows up all over every C++ code base in performance-critical parts of code, and the compiler struggles with it. Is this a question, or do you see the memory here? No, the memory is slightly different from that. It's the this pointer for this compute method. If it weren't for the this pointer, we wouldn't need memory for any of this. But because of the this pointer, and because we're calling methods here, we have to put it in memory. Like, the IR generated for this is incredibly worse than what it should be. And you can take the same code, right, and you just restructure a little bit, and you can take all of these things out, right? And now we can kind of reason about this and do much more interesting things. So if at all possible, try to minimize where these abstraction boundaries collide, because it just makes it really hard on the optimizer. But I want to give my little wrap-up bit, because we're running a bit low. Yes?
Can you show this again, because this is hard.
Yes.
It's not intuitive.
Sorry. So we have some code here, right? And we just call scompute. So essentially what this is doing, right, is this is actually setting up parameters in a struct rather than passing them to a function. And I'm suggesting passing them to a function, right? Because if there's like interesting bits of logic here, right, which would impact how we optimize this, we can reason about it, where we can't if it's in memory. Where C is like a constant.
And the main problem is that the compute, or the main advantage is that the compute takes S by value.
Yes, precisely. Right? Once it takes it by value, we don't have to reason about this pointers to like an aggregate somewhere in memory. All of a sudden that goes away. It's no longer a method. If it gets inlined, maybe we'll get lucky. But what if it's a bad inlining candidate, right? Like compute is big. That's the whole premise here, is that compute is big, right? But there's this interesting predicate that we can hoist out where we can actually do interesting folding with these expensive to compute things. But we don't know whether we want to hoist it out when it's stuck in memory. Anyways, this is a bit of a contrived example. I know this isn't the... Well, there may be. We don't know. It depends on the context, right? And the thing is that putting it in memory hides the context. Does this apply to const methods as well? Yes, sadly. We can have a great long debate about how const is or is not beneficial to optimization. Right now, I'm not aware of any compiler that really does aggressive optimization based on const because there isn't a whole lot you can do. There are like 2 cases you can optimize on effectively. I know that we're trying to add optimization for them to Clang and LLVM. It's very hard to optimize on, and the benefits are not what you would expect. In particular, const qualified methods have no utility whatsoever for the optimizer.
What about constref parameters?
The question is, what about constref parameters? Those also have no utility to the optimizer whatsoever. Both of those can be const cast away, so they're meaningless to the optimizer.
Because we are told in C++ pass by constref instead of values.
The comment is passed by const reference instead of values. The const isn't relevant here for the optimizer. When you have a reference versus a value, you have to make a trade-off, right? Is it better to copy the data in, or is it better to pin the data in memory and avoid a copy? I think people often undervalue the cost of keeping data in memory.
You say it's not useful to the optimizer because it can be const cast away, but doesn't that imply that if there's undefined behavior?
Not at all. Const cast is well defined. We can rat hole on this a whole bunch, but I suggest that we not. Trust me, it doesn't help. Find me later. I'll happily discuss it in all of the glorious details. A question over here, briefly, hopefully. How do you limit how much you optimize? Oh, there are no answers here. All of the answers are bad, right? We try to optimize as much as we can as fast as we can. And we try and finish optimizing as quickly as we can because there's a human being waiting for the answer. There literally are no good answers to this. Much like phase ordering, compile time trade-off versus improved performance is like the other kind of like, we don't really know what to do here. It's hard. We have heuristics. We have guesses. I'm gonna make you guys wait until the very end. I want to at least get my conclusion out, which I know you guys have been waiting for. I don't actually have a conclusion here. So the point of this talk is not to try and tell you, here's the silver bullet. You do this, you get good code. That's why the talk was not called How to Write Your C++ Faster. The point of this talk was for you to understand how the compiler is optimizing your C++, right? At a high level, to have a framework to think about how the compiler interacts with the code you write, so that when you interact with the compiler, it's in a productive way. Right, so that you leverage the compiler to do what it's good at, and you don't get in the compiler's way when you need it to do something for you, okay? That is the point here. I really, really want to see programmers and the optimizing compilers collaborating on making incredibly efficient code. It's too often that, like, as I mentioned at the very start, you're sitting there fighting the compiler, right? That's what I want to move away from. So that is actually the only real conclusion here. If you want like a rule, like I've mentioned a few times, pass by value, it's goodness, right? It's not a silver bullet though, right? There isn't one. You've got to think about the trade-offs. And now I'll take what rest of the questions fit. We have, I think, like 7 more minutes. There are also microphones, and so if you guys want to, do you want people to queue at the microphone? And then we will have much shorter round trip time, as I don't have to repeat your question. Or if you're too afraid to stand up, I can just like try and repeat questions. Okay, I will repeat questions. Yes?
What about the separate compilation model? Does it reverse the
Yeah. Oh, yes. The question I promised I would get back to.
So also I wanted a follow-up. How much can we do with link time optimization?
Okay.
Can we do something also with runtime optimization?
Okay. Okay. Yes. So there is another problem and limitation for optimizations, which is the separation of your code into different translation units, different files that are compiled separately. And the optimizer, can't trivially see between those two files. I didn't talk about this because I don't really view this as a fundamental or really interesting from a theoretical perspective problem. This is about how we pragmatically structure our builds. So there are techniques to solve cross-module optimization. You mentioned some of them. For example, you can have link time optimization, which actually builds this LLVM intermediate representation, but does not finish optimizing it, preserves it across all of the files you compile, merges all of them together at the very end, and then tries to optimize them very heavily. It's a great technique. It tends to have scaling problems for very large applications. Unless you have very large applications, and if you care about cross-module optimization, I think link time optimization is the be-all, end-all. Do it, forget about it, forget ever to think about cross-module problems again. There are other techniques as well. GCC has a cool technique called lightweight interprocedural optimization, which actually uses profiles to cherry pick pieces of IR from different translation units and merge them in to get cross-module optimization. Google contributed to GCC. It has very, very, very significant performance improvements for our workloads and our code, and it scales much better than link time optimization currently. There are also a bunch of other techniques. I could list them forever, but I don't know that it's useful. The only other thing that you did mention that I want to address is runtime optimization. So that was actually what LLVM was theoretically built for. Chris Latner's master's thesis was on lifelong program optimization. The idea was that you'd actually build a JIT into your program. And as it ran, it would collect profiles, and it would re-optimize the program as it was running, much like the JVM does, right? The hotspot JVM is kind of the famous example of this. It turns out to be a lot harder to implement in practice than it sounds, especially for a language like C++. You really need something like a garbage collector attached to make it really, really effective. I personally don't see a lot of run room there, but that's my biased view. I like statically compiled languages. Yes?
You mentioned that you admire the Eigen library. So if you're really into performance, I just suggest that you take a look at the Blaze library, which is truly probably the best performing library.
Which library?
The Blaze library. So they do not just use the power of a single core, but truly can unleash the power of the entire CPU. But okay, there's a question also. These guys who seem to truly know about performance do a lot of manual unrolling, manual vectorization. So apparently they don't trust the compiler too much. So what's your take on that?
How do you define people who know a lot about performance? Serious question. So I work with Google's optimization team, who's responsible for making our C++ code run fast. And I have never seen them manually unroll a loop. They also have access to the compiler, and they change it. I think a lot of the manual optimization stems from having a compiler you don't control. And this is why I would encourage everyone in every organization in the entire world to use an open source compiler and to use an open source compiler very near top of tree, so that when you want to change how the compiler works, you can actually go and write a patch to that compiler, get it submitted, and then you have the compiler working the way you want. It is the best way. Seize control of your fate. That is the beauty of open source. Minor plug. I'm going to keep prioritizing the folks at the microphone, but if we run out, I'll come back to you. Go for it.
Okay. Every now and then we see an optimization and we wonder, why did that happen and why did it break my code? Usually, I personally assume that the compiler is right, although they have bugs sometimes. And I now want to understand, why did he do it? Is there a way to get more information except for my code failing? This
is a great question, I swear. You guys are awesome plants. So what do you do when you compile your code and like the crazy cool optimization causes your program to stop working, right? Is it a bug in your program? Is it a bug in the compiler? Who knows? Even if you know it is a bug in your program, how do you even find it? This is why I'm such a big fan of the sanitizers. I don't know if you guys have heard, how many folks have heard of the sanitizers? Good. Okay, so the sanitizers, right, for those who aren't familiar, right, they're tools that help you catch bugs, right? For the folks on YouTube, they're tools that help you catch bugs in your source code. They do it by actually, when you're compiling the source code, they insert checks for bugs, right? Now, one of my favorite tools here is the sanitizer called UBSAN, or Undefined Behavior Sanitizer. And so what it does is it tries to go through all of the undefined behavior in the standard and actually check for it before it happens, right? And when you have something like that, you can almost always spot the bug in your code, right? So if you have code and you're really, really worried about the optimizer breaking your code, and you think that your code is correct, run it under the sanitizers, right? All of them, right? And you're going to find the bugs in your code. Once you have code that's clean on the sanitizers, then you know you have a compiler bug. Doesn't matter whether it's actually like your code has a bug or not, because either the sanitizer should have caught the bug in your code, or the compiler shouldn't have optimized that way. One of these two has to be fixed in the compiler. That is our specific goal with LLVM, is that we really, really want to have a strong guarantee that, if we don't sanitize for it, we aren't going to optimize based on it. That's our end goal.
Just one add-on to this. We got once bitten by devirtualization, where something was devirtualized which shouldn't. Is there also something to find?
Yes, so the question is, so for example, one of the sanitizers is a dynamic type checker, which will try and check whether the object is actually of the dynamic type you're accessing it as, right? And that will find bugs where you're actually accessing the type with the wrong, like you're accessing memory with the wrong type, right? And devirtualization would be incorrect, would expose this bug in your code. But there also may have been a compiler bug. I have no idea.
Okay. Thank you.
Like, compilers are actually software. I know it's kind of it's a little bit terrifying to think about that, right? But they are, in fact, just software. They have just as many bugs as all the rest of the software out there. Sorry. Go ahead.
Okay. My question is, if I force inlining with a compiler intrinsic, does it mess up your other inline pattern matching?
Yes.
Yes. So don't do that.
Please. File bugs when the inliner does the wrong thing. Understand that the inliner currently does a lot of things wrong. Last question, I think, because we're at least at 12. I'm happy to stay up here, but I figure someone's going to want to get lunch. So
very similar to this one, I've seen code where basically every function was annotated with force inline, and it has been very hard to convince the author that this may not be optimal. So can you give, because it's also not so easy to Google on the internet to find examples of where inlining has degraded performance of code. Can you give any interesting example that you've come across where this thing has really diminished performance?
Where inlining hurts performance. Sure. So the classic example is, imagine that you have an assertion library, but like a rich, like runtime assertion library that, whenever you hit some invalid state in your program, you construct a nice log message, right, to kind of log it, to like report it. Maybe someone's monitoring those logs, can get paged, right? If you're writing very large server software, which I have a little bit of experience with, right, you might have a lot of these. Like, you might have more of these than you have of other code, okay? Most of servers are like logging and assertions. Now imagine you were to take all of the code that you use to build up that log message, right? And you were to inline all of it into the actual business logic. Now, the only time that we're going to use any of that code is when your server has hit an error and is about to explode, right? Inlining all of this code into your business logic is going to slow it down. Great example, right? And so, for example, if you have a standard library, which has always inline or force inline annotated throughout the standard library, such as LLVM's standard library, right? you would see a lot of problems where you would use the standard library in these kind of, very unlikely paths, right, for error handling, and you'd have massive amounts of standard library code showing up in the middle of your program. I mean, maybe the compiler can fix it for you, but eventually it's going to fail, and you're going to have a performance regression. The hard part about finding performance regression examples here is that the primary penalty from inlining is code size growth, which means that in order to have an interesting example, it has to be big, right? Which makes it not a good example on Stack Overflow. Okay, we are into lunch. Like, it's your show. Tell me when to get off the stage. Okay. Thank you very much.